this training is derived from our quantum series of training. And so what I want everyone to understand here is you could certainly take this. After this, you'll get emailed a PDF copy of this presentation. Plus, you're going to get a link to a quiz you could take. Now, that's going to give you a little bit of RUs. Probably, I think it's a half RU credit. That's a good thing. But if you want to take the entire quantum class, we have there's video training in there. There's gain structure. There's AEC. This is a blend of gain structure and AEC, and we're going to do that first. So the idea of these classes were to give Q-SYS installers a better understanding of gain structure and how to get the best audio performance out of a Q-SYS system, right? So it's important to set gain structure as a basis for all audio coming into the system. And then the other thing people forget about is the audio that leaves the system. So that's something to think about as well too. So the other thing that we got to remember too is garbage in and garbage out. If you're not familiar with that term, I guess we could call it GIGO, like G-I-G-O, is if I'm taking a dirty, bad, noisy, low-level signal in, there's only so much we're going to be able to do with that. DSPs are magical in some ways, but they are not magical, and there's no magic way to fix bad signals coming in, right? There's some things that we just won't be able to overcome in the DSP, and we'll talk about what that is. So with that being said, proper gain structure is a key component, right, to getting the best performance out of your Q-SYS audio system or any audio system, right? So bad input levels or improper dynamic processing will affect the entire signal chain. And so I think it's important for everyone to kind of just start with that as a basis, and just look at this as a signal chain, right? So we're going to calibrate our inputs. We're going to do some type of system conditioning or input conditioning to the signals. We're going to add user controls. And yes, we could have probably a whole hour-long debate on whether user volume controls go on this side of the mixer or that side. And it's a preference. We're not going to get down into the weeds in that. We'll talk about the pluses and minuses of each way. And then, how we mix microphones together, how we mix program audio together, and then the output side, right? So what are we outputting to? And we're going to want to know what we're outputting to, because that's going to affect how we set up the outputs on these cores if we're not going to one of our digital amplifiers or something like that. So let's start getting into just some of the language of audio, right? So the very first term that we want to talk about is noise floor, right? So what the noise floor is, every circuit is going to have some level of noise that's in the bottom, it's on that input, whether you're there or not, whether you're using it or not. So that's just the noise being associated with a circuit being used, right? The dynamic range is the allowable signal range between the noise floor and the point in which the signal clips. Now, in this slide, you can see that plus 24 dBu is the industry standard for a clipping point. And that in this particular example, say the noise floor is sitting at -81. This obviously, it doesn't have a microphone plugged into it. This is just an open input, or maybe this is something prior to a component before that. So between -81 dBu and plus 24, we have 105 dB of dynamic range. So the area between the noise and the clipping point is going to be the dynamic range. So the next term that we want to talk about is headroom. So headroom, it generally takes a 10 dB increase in the SPL to be perceived as twice as loud, right? So if we're looking at that, so if we've got a signal, so ideally we want to have at least 20 dB of headroom on our signal that we're reproducing before it gets to clipping point. So that's where we start coming in with this nominal level, right? But we end up with what we call a signal to noise ratio, which is actually the difference between the noise floor in there and then the nominal level that we're looking at. So the overall may have been, 100, 105-ish, but now we're going to get down to, when we're talking about the signal to noise ratio, that's going to be from the nominal level that we set our input to and the noise floor there. So signal noise ratio is that we want our input to be sufficiently above the noise floor, and we'll talk more about that as we go along. Nominal level, like I briefly mentioned, is that sweet spot, right, where it gives us the ability to add it have up to 20 dB spikes in the signal and levels. and still be able to accurately reproduce the signal. In professional audio, most of the things we deal with in Pro AV, +4 dBu is what's seen as the nominal level. In consumer line level, it's not on the slide, but in consumer line level, 10 dBu is nominal, negative 10 dB, I'm sorry about that. And then microphone could be as low as 10 dBu or -60 as well. There's really no standard for microphone for condenser mics, as their levels can vary quite widely depending on what else is going on in the microphone there. So then we start talking about some other terminology with audio here, right? The preamplifier circuit. So preamplifiers allow us to help the input signals coming in get to a desired level, but especially for like microphones, but like Q-SYS and most DSPs will make use of an analog preamp circuit, which generally will provide the lowest noise sample to the DSP, right? Because when we're in a digital, we have to bring this into a digital world. So we're bringing an analog signal in. It's going to go through an analog preamp and add gain. We're going to be able to add gain to get this up to the signal that's coming into a nominal level. And then we're going to send that to the analog to digital converter. And then after that, we will be able to adjust it with the digital gain. So the idea, back to garbage in and garbage out, is we want to present as good and healthy, clean signal at the right level, close to that nominal level of negative or of +4 dBu, to hand that to our analog to digital converter so it can do its work there. And then the next thing we want to look at is digital systems sample the analog waveform, right? And then the sample value is scaled in comparison to the ADC supply voltage, right? Understanding this conversion actually requires another, what's the word I want to use? Label that we use on there and terminology on that. So once we go through the analog to digital converter and we're in the digital world, now we're going to be measuring things in dB full scale. So DBFS, and you'll notice most meters in Q-SYS, and we'll see this in some of the slides coming up, will show DBFS. Now, if you're new to the product line and you're used to using other DSPs, some DSPs will have their nominal level be set at 0 or at +4. They might be looking at dBu. In Q-SYS, we use DBFS. So what you're seeing after the fact is, so that's going to make a big difference, right? Because +20, if you're going for 0 on a meter that's dB full scale, you're trying to set your input levels at peak. So you're actually going to go back to -20 DBFS in there. So this next slide kind of goes over that a little bit better, right? So the idea here with dB full scale, if you looked at our input, our input blocks here, this, when you adjust the preamp gain, it's telling you how much dBu it is. But what this meter is actually after the analog to digital converter. And so you're getting this level. This is a dB full scale level. Even this is what's happening to, this is the amount of gain you're adding. And then this is the actual level post digital conversion there. So what you're going to want to do is for every input, you're going to want to increase the gain, the preamp gain down here till you get a level around -20 dB full scale. And you're going to want to do that for every input. I can be honest and say that, early on in my DSP career, I'd be like, oh, I'm going to test with this, I'm going to get a couple of these at the right level. You need to make sure every signal coming in is hitting that standard level. That way, when you go to a mixer, things are looking the right way. We'll talk a little bit more about that when we get to mixers. So microphones, introducing microphones, ambient noise that's in the room effectively becomes the noise floor. Prior to this, when we're looking at like a -81, that's definitely not an open mic in a room. That, you're typically going to see levels much higher than that with a mic. So when you need the signal level of each talker to be sufficiently above the noise floor to ensure that we have good speech intelligibility. So the first thing you're going to want to do is you're going to want to achieve a nominal level of -20 dB full scale when someone's speaking at a normal level and distance into the microphone. And I know that's always a challenge, right? You don't want to test your microphones with hello, hello, a big booming voice, because that may not be indicative of how everyone's going to talk in a meeting. So you want to set that level. So you have someone speak into the microphone at a normal distance and a normal level, and make sure that you add preamp gain till you get to that nominal level of the talker. Now, you want to make sure that at that point, we want to make sure that the signal noise ratio is at least 15 dB above that when the microphone is open, right? And we've got a couple slides that go into that. If the microphone is unintelligible, there's no way to fix that, right? So if we're getting a really garbage signal in, we're just not going to be able to process and do that. There is a noise reduction component in the AEC algorithm, and we'll talk a little bit about that further on in the thing. But the idea of that AEC algorithm is just to reduce steady state noise from, say, a projector, a fan, other things that are constant noise. It's not gonna, get rid of somebody that's a loud talker in the office next door, or somebody that taps on the desk or coughing or crumpling paper. The AEC doesn't do anything without that. So, but poor signal to noise ratio has to be addressed at the source. So if we take a look at this, if this was our noise floor, this would not be acceptable, right? So if we have a nominal, what we want to do is, if we have a nominal level of negative 20 dB full scale, we want to stop talking. First thing we do is have someone talk into the microphone at a normal distance level, adjust the preamp gain till you get to negative, have them stop talking, and then let the room go silent. If the meter is not below negative 35 dB, if it's not something below that, then we are not meeting the minimum signal to noise ratio for speech intelligibility. So what you're going to want to do then is you're going to have to address that at the source, either get the signal cleaned up or change maybe positioning of mic, right? But what does it look like the right way, right? So if we set a nominal level at negative 20 dB full scale, and then we stop talking and go quiet, and we look at this meter, it's down at negative 42. It meets that 15 dB of signal to noise ratio that we're looking for there. So anyways, that's the important thing to set there. That if you get anything out of this class, that just this first 5-10 minutes here of talking about the fact that our meters are all in dB full scale is a big plus here. But let's start talking about things that are in our signal path, right? So in a typical microphone signal path, we're going to have, you might have a high pass filter, you potentially will put a parametric EQ in there, and then a low pass. This is a very common signal that you'll see there. Now, signal chain that you'll see. High pass, typically with microphones, you'll cut off the frequency somewhere between 60 or 80 hertz, maybe even up to 100 if you need to. You can use any type or any slope. Those are all your preferences. We're not going to dive that deep into the nuances of of a Butterworth versus whatever other types we might have in there. And then the parametric EQ, this is a tool that you'll put inside next in your signal chain. And you're going to want to notch out any components that are recommended in your microphone EQ. And you may even do some of the EQ for the room for that microphone in this parametric as well. And then the last piece in the chain would be a low pass filter. So the parametric will remove any frequencies that are causing feedback or problem. And then the low pass, you can do that around 16K. You could even bring that down as low as 8K if you wanted. It's going to start to sound a little old school telephony when you start bringing it down a little too much. But the idea is to trim that low end off of there. That's the human voice doesn't quite go at a 16K, so we're fine. So the next thing you do would consult the microphone manufacturer for his recommended curves, right? And use the separate EQ components to EQ your mic and then EQ for your room. So I like to clarify that a little bit and say that you EQ in this first signal chain of the mic is where you would put notches in to keep the microphone from feeding back in the space. But then you might have another parametric on your output side that you use to actually EQ for the nuances of the room, for all the audio, for how it sounds and things like that. So just to do that. Also, sometimes you may have to put little bumps or notches. Typically, I like to subtract only with a parametric, but there are sometimes you might need to bump. Vowels typically land between 250 and 1,000 hertz. Consonants are between 1,500 and 6,000 hertz. So Your S's, your T's, your Z's, those actually happen between 5 and 8,000 hertz. So that's why sometimes on POTS telephone lines, you'll get where people will lose that T or the Z. I have an S at the end of my last name, Waltons, and a lot of times people miss that S in there. So just some FYI there. So the notch feedback controller, so you can also add a notch feedback controller to the input signal chain, and then you can make some noise, right? So this is a tool that we can use in here. You set their fixed filter count to 0, set your dynamic filter count to 5, a minimum frequency to 80 and max to 20K, and find the threshold of where you're getting feedback, right? So it's an ad hoc way. We can, a lot of people, I teach this in level 2 a lot, and people are like, well, if you EQ the room right, you don't need a feedback control. Yeah, that's true, but there's also sometimes there's unmanned that that have unmanned don't have an operator in the space, and maybe amateurs are using the equipment, or things like that. So there are places where it's used, but one thing you can use it for is just a tool. Put it in your test kit, and use and be able to go through and EQ, use it as a tool to tell you where things are feeding back. So if we kind of take a look at what that looks like in here, if we were to be running this notch feedback controller, and like you said here, it says set the fixed filter count to 0 and the dynamic filter to 4. And we're not going to dive deep into the NFC, but these dynamic filters will go away after X number of seconds. In this case, it's set to 30, but you can see the minimum and maximum dynamic frequency is set to 80 and 20. Now I'm going to point out to you, this minimum frequency is this little line right here, this dashed line and this blue dot. And then the maximum frequency is over here. Now, out of the box, this thing comes out with the min and the max set at 1K. So you will get no dynamic, it will listen to no part of the signal, because it starts at 1K and ends at 1K. So when you bring the notch feedback controller out into your design, you want to open that up, because you may only want to notch feedback between 200 and 2K or something like that. You may want to do that. So anyways, that's kind of what you're going to do there. And you can see in this case that we have problematic, these are the areas where it's feeding back, is at 150, 210, roughly 600, roughly 800. So how would we fix that? Well, what we recommend you do is you go back one step, go back a couple of blocks in that signal chain to your parametric, and we go ahead and we open up the parametric EQ and we put in a couple of little bumps. Now you'll notice if I go back a slide, those are like 10, 12 dB, notches that the notch feedback control, because it's a big, it's a big lug. It's just trying to stop the feedback. We can be a little more nuanced when we're dealing with the parametric EQ. So if you notice, we just take a few dB out of that, and then that's probably going to be enough to attenuate that signal there. And then you can test it by going back to the notch feedback controller, hitting clear frequencies out. So you can go down here and hit clear dynamic. You'll hit that button, it'll clear them all out. And then you can see if the notches that you put into your parametric are actually taking care of that. So that's kind of what we do there. I thought I saw that we had somebody's hand up. Did they already drop that hand, or did we have a question come up? Nope, we're good. All right. All right, here we go.
Just to pause you real quick, Dan, I've been asked
Sure.
several times, can you leave that notch feedback filter in?
Yeah, you absolutely can. No, that's there's no reason not to. Now it does, it uses you want to know, because it has certain, it's going to use up resources. I wouldn't leave a bunch of them in a design. But by all means, if you want to leave it in there, all you need to do is you can bypass it, right? Oh, I need one more slide. Here we go. There we go. You can just bypass it here and leave it in, or you can leave it active too. You may want to set it to where, you only have a few filters. It'll allow you to do up to 32. If you put 32 filters into a signal, it's going to sound horrible. So just kind of think about what you're doing there. That's all. So, all right. So let's move on to talk about mixers. So two major types of mixers, right? We have a matrix mixer. In Q-SYS, we don't have a standard mixer or a mono summer. we have a matrix mixer. It has inputs that can be configured as with mono and stereo, outputs with mono and stereo, and the user is going to, in a matrix mixer, the user is going to assign what input goes where and what output level is simply mixed to that output, right? Now, auto mixers, slightly different. Primary function of an auto mixer is designed to have a room function without someone working a mixing console. It should require no operator, but the mics get mixed to a single mixed output, but all of our auto mixers also have optional direct outs that will contain the corresponding signal. Now, two major algorithms decide which mics pass the output, and we'll talk about those two in just a minute here. The output level, the whole idea though, is with an auto mixer is that you're keeping the output level of the microphone is consistent. So this would be good whether you're on a conference call, right? So if you're mixing a bunch of microphones in a room on a conference call, you don't want the far end, if a couple extra people start talking, getting a louder volume, you want it to be controlling that. Same thing as if I had several microphones on a dais and they're speaking into a room. I'm going to kind of share that gain between the microphones because I don't want, as more people at the table start to talk, we don't want the volume in the room to run away. So that's the idea with the two. So let's take a look at the matrix mixer.
Dan,
Go ahead, sir.
we do have one question about the notch feedback filter.
Sure.
And I'm not 100% sure. Can you use it with probes?
Yes, you absolutely could probe into it and probe out of it. Yeah, that's a great way to do it. You could also throw it into, if you've been to level 1 and level 2, you can put it in your test kit and then probe in and probe out of it as you need to. So yeah, great question. So cool. So the matrix mixer, you bring all your inputs in, assuming all inputs are adjusted to nominal on your input side. So back on the inputs, the mics coming in, the program audio, all of that. If all of those are adjusted properly, this should not look like a random bunch of crazy numbers, right? Everything in these cross points should be, for the most part, there may be some special use you're doing, between +6 and -6, somewhere in there. I mean, you shouldn't be all over the map when you're inside of this here. If someone sends me a conference room file and they're like, oh, we just can't get the AEC to work right, we're getting reflections, and I open up the matrix mixer and these cross points are all over the map, I say, you didn't do your proper gain structure on the front end. And we go back and fix that. So that's a key element. If you're having to add 10, 12 dB of gain on a cross point, or you're subtracting a bunch versus something else, you probably don't have your gain structure set right. So just know that. You also can go in here and you can enable in the properties of Q-SYS Designer mutes. So you can just mute each cross point if you need to. So that's one thing you can do. Auto mixers used mostly for conferencing and speech reinforcement. They do an adaptive threshold gating. So the maximum number of mics open, our suggested range is between 1 and 3. And I love it. Matt Gray in our support and dev team used to say, well, if we have more than 3 people talking, we now have an argument. It's not really a meeting anymore. So I use that as a rule of thumb there. So but the number of open mic settings should remain at default. So I think we default at, or the attenuation settings, keep those at default unless you really need, if you're working with support, you need to do something there. But the idea here is, so even if you're doing a larger room, you still really only want about 3 microphones. So I've had people like, well, I've got a 3-way divisible room. Do I want to, have a nom of 3 in each room? But that's gonna be a total of 9 mics open. You're not going to want to do that. So maybe 1 for each room, or one big matrix mixer that handles all of it. The other thing too is you've got these manual buttons in here, which allows that channel to be removed from the auto mix, right? So no matter what, that microphone is always on and there. So if the most important person in the meeting is always at the head of the table, we may want to take that microphone, set it to manual, and then maybe instead of setting our nom to 3, we might set it to 2, knowing the 1 mic's always going to be open, and then we're going to let the auto mixer open up 2 other microphones to be in companions with that. So if we look here, we have 1 microphone open. We have no attenuation being done at all. If you look over here in the attenuation side, we have it set to 4, but the only reason it's to 4 is so that you can see what happens as we continue to go on with this. So with 1 open mic, there's no attenuation going on to the outboard signal. When we go to 2 open mics, you'll see that we're adding a little bit of attenuation. We're adding 3 dB because we're taking those 2 signals. We got 2 mics open now. We're adding some dB. We're subtracting from the output level. Now, when we go to 4 mics, you can see that we've added now 6 dB. And you can imagine that if this was a 18 mic mixer, as you added more mics, and if you had a larger number of open mics, you would keep attenuating that down. Now, for conferencing, I am a big fan of the gating mic mixer. Now, when we move into gain sharing, I prefer to use gain sharing mixers for if I'm doing a dais. Now, if you're doing less than 8 microphones, I think gain sharing might work fine for you in conferencing. At that point, it's what you're most comfortable with, but I find the gating mics work best for me in there. And then when you're doing a presentation space or something like that with multiple mics, use the gain sharing. The idea of the gain sharing, ours is based on the Dan Dugan gain sharing algorithm. It's not licensed as a Dan Dugan gain sharing algorithm. Its maximum gain is of 0, okay? And open mics will share the available gain there. So you can see every mic, in this case, no mics are open, so all of them are essentially turned down. So there's a negative gain applied. And as we open up, as one microphone opens and starts to talk, it gets granted all of the gain that's available there. And then if we go to 3 open mics, you can see that it's granting more and more of that gain across the whole space there. So anyways, it's great. Each mic is granted less, works well for systems with fewer mics. And like I said before, gating auto mixers definitely for any mics systems that go over 8 to 12 microphones. So let's put it all together. We often need both matrix and auto mixers in the same signal flow. Note there are no user controls for microphone levels in here. We do not. I mean, you might have a gain control in here for internal, but you would never give that to your customer, right? You should never adjust your gain level before it goes into the gating auto mixer or a gain sharing mixer. So you don't want your end users to be essentially messing with your gain structure. So compressors, when we start talking about microphone dynamic processing, compressors will primarily level off any loud talkers that you have. And then they can be aggressive sometimes for just spoken word. They're less aggressive when you have a vocal performance or someone singing, right? That's where they work. They're less aggressive or less heard, but they still have function there. Drawbacks of the compressor is they don't solve any issues for quiet talkers. So automatic gain controls, we do have an AGC. It does help with quiet talkers. They can be tricky to calibrate it, and it does help for loud talkers too. So it's a little slower to react than a compressor. And once again, if you don't set it up properly, it's going to increase the level based on noise there. Typically, I will use a compressor if I need to in a case, but kind of a lot of that's proper mic setup and all that too. What's wrong with this picture here? Well, you've got a gate in front of a gating auto mic mixer, and I will not lie to you and say I have tried this before because I had a noisy signal that was getting noise induced on it because of the conduit it was going through with other stuff. And I'm like, well, I'll just put a gate on it before the gating mixer. Well, no. I should have fixed the mic, and I fought it and was back to that customer several times and all of that. So, just don't put a gate before a gating auto mixer. It should be looking at as clean of a signal as possible. Should not be altering it there. So, all right. So, next topic here are let's see, introducing AEC into our system there. So, just one moment here. There we go. So when we introduce AEC, this is specifically for conferencing applications here. Let's start with terminology. So latency. So it takes a little while to remove the AEC reference signal, right? So we need some look ahead time, right? So our older algorithms were running 13.3, and you'll find that in the older processors, our Core 110, the 8 Flex, the Nano, those are going to run up to 21.4 milliseconds of latency. All the larger cores are going to be 10.7 milliseconds. Look for some updates on that. I think the 24F and some of the new processors may be slightly different. And if you tune back in the coming months, I think I've got this deck in progress of being updated, not only with new marketing glitz, but also some of the updated processors and all that. The other word that we're going to talk about is tail length. So if you're not familiar, AEC components listen to the signal for a given amount of time, and then they try to subtract out based on the reference that they're giving. In Q-SYS, and I still believe to this day, we're the only one that gives you the user the ability to adjust the tail length. So the industry standard for tail length on AEC components is around 200 milliseconds that's kind of the industry standard for effective AEC. In Q-SYS, we only give you the ability to set it to 100, 200, 300, or 400 milliseconds. And what that does is effectively it adjusts how long the FIR filter actually functions. So the longer the tail length, the more DSP resources consumed. Now, I will say this. When we tell you, I'll say Core 110, because everyone's mostly familiar with that. When we tell you that a Core 110 will do 16 channels of AEC, that's at 200 milliseconds. If you have to take those AEC, if you have to take all your channels to 300 milliseconds, it's going to limit you. You're only going to be able to do 12 channels of AEC. And if you have to go to 400 milliseconds, that processor is working even more. The memory resources are being used up. You're only going to be able to get 8 out of the 16 there. But the bonus is if you had a very well acoustic treated room, or you had a microphone, microphones properly placed, and people who had good microphone etiquette and meeting etiquette, you might be able to get away with a 100 millisecond. But I would never design a system based on knowing that using 100 millisecond AEC. But it does add how many AEC instances you can put in your design. So typically start your design around 200 milliseconds. That's the industry standard. So RMLR, so the reference to microphone level ratio. This is the difference in the level between the reference signal and the resulting signal that's at the mic. So if you know in AEC, we always come back and we add a reference that gives us what is actually coming out of the loudspeakers, right? If you think about a microphone, let's just say a basic table microphone. If it's sitting there on the table, it doesn't know the difference between my voice and the audio coming out of the loudspeaker. So what we do is we take the audio that's coming out of the loudspeaker, that's being sent to the loudspeaker, and we send that back as a reference, right? So we're bringing our actual microphone signal gets brought in, we bring the reference into here, and then it comes back and sends that out. And so that's expressed as a loss. So your RMRL would be negative 20 dB, which is what your reference might be coming in at, and your negative 30 dB coming in from the mic, so you would get a 10 dB there. We'll look at the meters and actually do that there. This is also known as echo return loss in non-QSC DSPs. Residual echo suppression is the same as nonlinear processing. It removes any error signal after that convergence has happened. Voice lift. In large rooms where near-end microphones are sent to speakers in the near end, that is called voice lift, right? And so the example I use with that is I recommend using, we have sound reinforcement outputs out of our AEC block, and there's a lot of contention on this, but the guy that wrote the algorithm said, use the sound reinforcement outputs when the microphone is never going to be in the signal, in the path of the loudspeakers. So for instance, if I'm on a stage with speakers on either side and there's a possibility that that microphone is going to be in and out of that, or if I'm doing a mixed minus system in a room, you want to avoid using the sound reinforcement. Now, if I've got a lapel mic on and I'm at the front of a room and in the back row of the room, I'm lifting my voice to that back row of speakers, that's a great application for the room for you to use the reinforcement output. So typical pathway here, path to the far end, the local microphones go into the AEC, then they go into their auto mixer and they output to the conference output. I wish every conference system was this basic. And then path to the near end, so the path to the room you're in there is any program sources you have, and the far end conferencing coming out of the VoIP. This could be VoIP, this could be USB, whatever, same thing here. So we're going to mix our mics, gate them, and then we're going to send them out to the output to back out the whatever we're using, whether that's POTS, VoIP, could be USB, whatever the case is. Speakerphone. And then over here, same thing. We're going to bring that audio back. We're going to mix that together, and then we're going to send that out of our amplifier out to our loudspeakers. You'll see that we got a tag here coming off there as a reference. Now, if for some reason we had gain controls post mixer, we would want to make sure that that reference lowers and raises with that as well too. So if we look here, typically what we will do inside this channel group here is you have a high pass filter, a parametric EQ, low pass, and a compressor. The channel group, I'm not going to dive super deep into that, but it's just a great way to put a lot of different components together in there and be able to have it apply it to multiple signal chains there. But we'll typically apply your compressor or AGC for level consistency, and then go into your gating mic mixer there. Best practice is apply these after the algorithm if you have to. So you'll notice here that we're not applying anything before. There are some times where you may find, I know early on with some of the beam forming microphones, it was imperative to put like a really big high pass, or put a big high pass filter somewhere around 80 hertz before you went into the AEC, because some of those early on, some of their algorithms were getting that out. But that's typically the only time I've had to put any kind of dynamics ahead of the AEC. So you can, if you have to, put them, but nonlinear objects, never put nonlinear objects in there like compressors or anything like that before the AEC. So the most important factor in successful AEC is having the correct reference signal. So when there is no voice lift, the adage is what goes to the speakers goes to the reference. So all of the far ends, the program sources, especially if they're being routed to the far end, and never put a microphone signal into its own reference. And that's a rookie mistake. And I know I did that early on in my AEC career of, well, I don't want this mic to have echo. And so you do that, and what's going to happen? It's going to be a very underwater sound as it's trying to get rid of it, if it doesn't completely get rid of it. So assuming that you've already brought all the microphone signals to -20 dB full scale, and you're achieving at least 15 dB of intelligibility, which would be something below -36 dB, right? And below. Set your amplifiers to a minimum level, or set the output block maximum RMS to -40 dBu if no controls are on your amp. Then you're going to want to use your preamp analog gain to bring all program source inputs to -20 dB full scale, and then leave your program sources at a unity gain. With a calibrated program source, bring up your amplifier or your max RMS setting to a comfortable listening level. Now, early on, when I first started doing conferencing and voice lift and things like that, I would, the human voice is about 65 dB, and that's where I would always set my rooms. And then I found that every time someone went in there to use it, they would, tap it up 2 or 3 taps. So essentially, 70 dB is just typically when people are in meetings, they want to hear the voice a little bit louder than what the human voice is to kind of discern that that's coming from the far end. Make a test call. Adjust all your far end gains to receive a nominal level. So we're talking about here the VoIP or the POTS or the USB conference. You're going to make sure that level coming back from the far end is at -20 dB full scale. So when you're listening at the far end, with listeners at the far end, the AEC can then be fine-tuned. You're going to want someone on the far end there. If we look at the AEC block here, the noise reduction is going to allow for you to, noise reduction reduces only steady state noise. We talked about that. It's not magic. And the more of that you use, it's going to color and it's going to affect the signal. So if you can, try to, with the noise reduction, try to use as little of that as possible, right? And remember, it's for constant noises. It's not for Bob the loud talker in the office next door. RMRL down here, this is one of the easiest meters to read in Q-SYS, right? What it's going to do is as it gets from down here at negative 10 or negative 10 up here, as it rises up, it's going to get greener and greener until the middle, and then it's going to start getting yellow and red at the top there. So it's really easy. You just want to adjust it till it's right in that negative, or when it's right in that green area right in there. So it's not green, reduce the reference meter until it's only the far end talking, speaking. The adaptive filter up here is for if you have to mute the microphones ahead of the AEC. Typical best practice says that you should mute microphones post AEC so that the algorithm can always be listening to what's going on in the room. And so in this case, what you want to do is you want to set the adaptive filter. If you have to mute the microphones before the AEC, what you'll do is set the adaptive filter to whatever the noise floor is of the room. So be quiet in the room, let the mics sit. If the mics are sitting at, the inputs are sitting at negative 50 dB, then that's where you want to set that adaptive filter. And it's essentially just going to kind of fake out the AEC algorithm and say, this is the ambient noise you should be hearing in there. So it's a little bit of a Jedi mind trick. And then the residual echo suppression. The way I look at this is after the algorithm does its job, this is where you can kind of dial in and tweak out any little artifacts. So once you've kind of got the room set up, you've got your gain structure right, you'll go through your RES and you kind of dial that up. Now, one of the things there is if you increase the residual echo suppression, you're going to approach a half duplex, which is not telephone. That would be more like a walkie-talkie, right? So you just want to be careful of that there. You also want to test for double talk condition here. So have someone from the far end speak and someone at the near end speaking at the same time, and make sure that you're not getting an echo or any weird anomalies at that point. So if you have too much RES in there, when you have both people talking, far end and near end, you'll hear some issues with that. So that's where you would adjust it up. That's if you have too much going on there. What if there's still significant echo? Well, we can make sure that the signals aren't misrouted or looped. That can sit and be there. This used to happen a lot with video codecs. I remember that with the HDX, I think it's 8000s and 7000s. If you didn't go into them and set them up, depending on which output you took, it could have the audio in there. So that could happen there. Mute your microphones to verify that it's really echo and not a direct coupling where you've wired something improperly in the design. If the echo is still there, mute all of your inputs and then start unmuting them to identify your misrouted source. What if there's still then suggest to the customer that they properly treat their space. No. So check your AEC tail length. So we mentioned AEC tail length. And so if for some reason you had it at 100, extend it to 200. If you're at 200, I wouldn't just immediately go to 300 and 400. Only really large reflective spaces are going to need that 300 and 400. And just think about it. If you don't have to do any complex testing, but if you clap your hands and there's, a lot of slap and residual echo in the space, then you probably are going to want to experiment with 300 and 400 milliseconds. But don't just magically, oh, I've got echo, jump right to that. Go back and use the other things. And then the other thing is reduce, make recommendations to reduce the reflectivity of the room. So conferencing call, so repeat the test call for each conferencing type, and finally make a call with all of the conferencing types. We don't seem to have a lot of that. I mean, I'm not out in the field doing installs anymore, but it seems like the designs I have seen and stuff. But there was a time when you used to set up POTS and VoIP and a video codec, and you had to make sure all three played together in case three different everybody came in from three different ways or what the bridging was. But still, best practice says to do that when you can. And let's see. So after the mix, we're going to want to add some equalization. Maybe we may or may not have user level controls. We're going to put any limiting or any delay in. So EQ in this output signal chain is typically to EQ for the speaker. Every speaker manufacturer will give you a curve saying, hey, to make this speaker flat or perform at its best, flat meaning just that whatever waveform you put into it is the same waveform that it reproduces. And that can, nobody builds a perfectly flat speaker. And then based on the room that you put it in is really going to have an effect on that as well too. So you can do some speaker EQ in there, and you're going to do a little room EQ, right? So you can add some curves and some notches in there for the reflectivity of the room or how it's reacting to the sound that's being put into the space. And then our user gain controls better at the input or output side of the mixer. Does the end user need to control all of the levels, right? So if they need to control the program audio versus the conference audio versus, if there's lots of different things there they need to control, then yes, you would want to put multiple user controls before the matrix mixer. If they don't need to do that, then just put one output post mix. Now just remember that your AEC reference needs to also go up and down with that output as well. The whole idea here is don't give your customers enough control to where they ruin the gain structure, right? So if I have gain controls prior to a matrix mixer, and I also have a gain control after the mixer, they could get that really out of whack. So just make sure you do that. Limiting prevents a signal from going beyond a predetermined level. It prevents clipping and prevents overloading of amplifiers or any other downstream devices, right? The peak limiter block is set at 0 by default, but let me just show you here kind of how that works, right? So you can see here, by default, it comes out the threshold is set to 0, meaning anything that goes above 0, we're going to limit that back down. We have a 10 millisecond attack time, meaning that's how fast it's going to apply this, and then a 100 millisecond release time. So if I have it set to 0 and my signal level rises, it could potentially overshoot that by, close to 6 dB. And so what we want to do, and so then it's kind of overshooting that. So what you can do to kind of prevent some of this is you come in here and maybe set this to play with this a little bit, right? Set it to -3, maybe set it to -6, but we're going to reduce that threshold by, in this case, by 3, which is going to allow it to, before that peak limiter goes fully into place, that we're bringing the signal. We're not letting it overshoot as far before that happens. And this question comes up a lot too. Like you'll see here, let's reduce threshold by 3 dB. So we reduced it by 3 dB, which makes us a -21 dBu output on the output. So you'll notice here on the analog side, on the line outs, it's measured in dBu. It comes in the digital world, as dB full scale. It goes through the analog to digital converter, and then we adjust that analog gain right here on the output side. So by default, they're set to 0, and you can turn that down. Also, one other thing on peak limiters. Peak limiters typically will use on outputs only. AGC is something you would use in compressors on the front end side. Q-SYS amplifiers, if you're using a Q-SYS amplifier, then the limiting in all of that is being done for you. There's lots of different limits when we configure them correctly. The digital amplifiers are going to give you a DAC limit, meaning the clipping stage before the amplifier, the digital analog converter. Protection, so if we happen to have a short condition or a speaker goes bad, driving low impedance, right? Low impedance means additional current, which means additional heat, which means additional current, which we go get a thermal runaway there. And then limiting is just based on load type. So when you use our digital amplifiers with Q-SYS speakers, you attach a speaker block identifying to the amplifier what kind of speaker it is. It might be an in-ceiling speaker, and I'm using it as low impedance. So it might show up, so I can set that up in its properties, and the amplifier knows, hey, this is I should set my output load for 16 ohms. I know that only this much power and this much should be sent to that speaker in order to keep it. So that's some of the benefits of using the digital amplifiers there. If you're not going to a Q-SYS amplifier, we ultimately must convert it back to digital audio, back to analog. And then in the limiting example, you saw clipping at 0 dB full scale. In keeping with our 20 dB of full scale structure, the gain should be left at 0. So at 0 digital gain, this is perfect for if you have a downstream device that is a professional downstream device, right? If we're going into a pro mixing console, whatever the case might be, you're going to want to just leave it set like that. But what if it's a consumer device, right? So let's say I'm going to a consumer recording device or a consumer amplifier or something like that. Ideally, I'm going to come in and I'm going to adjust this output gain to where I'm now outputting a little bit less signal, right? So I'm closer to it's negative 6.9 there, but we're shooting for consumer line level of about negative 8 dBU. So that's how we can do that there. Or actually, we now reach 7 dBU peak instead of 0 dB full scale. So you just kind of want to make sure whoa, how did that change? Oh, we missed one here, microphones. So sometimes you got to feed a microphone and you can actually turn the output gain down to where you're only, you're providing a very small signal going down there. If for some reason you have to come out of your Q-SYS core and into a mixing console that only has a microphone input, you could do that here as well. But let's talk about how that impacts it, right? So when you increase the output level, you're decreasing the signal to noise ratio. And so the idea is to have as big a signal to noise ratio as possible, right? So if we go back to those terminology that we talked about earlier on in the presentation, we said we have a noise floor, and then we have, if we're at professional level, we're at plus 24 dBU. That's a lot of difference, right? So this noise floor, let's just make it easy. Say it's at negative 50, right? We're going to have quite a bit of level there. If we have to change the output level down to negative 10 dBU, we're going to have even less, right? So where here we'd have 74 dBU. Here we would have 10. So you just want to think about what you're doing. It's always best to try to stay with professional gear to give you the most headroom and things like that. So let's review quickly the most important concepts we talked about. Calibrating your inputs. That's the most important things. In Q-SYS, we use dB full scale once it goes through the analog to digital converter. So we want to make sure we set all the programs, microphones, all of that. Conferencing system. Mic EQ, trim your high and low frequencies, right, with low pass filters. Use a parametric to kind of notch things out. And then you can also use a notch feedback controller to identify what your problem frequencies are in the room. Automatic gain controller compressors can be used to help get consistent levels from wide ranges of talkers on your microphones. And then auto mixers. We don't place controls or levels or gates ahead of auto mixers. We use gating auto mixers for noisy rooms or rooms with more than 8 to 12 mics. And then use the fewest user gain controls to get the job done, right? So you don't want to have multiple controls in the same signal path. It's going to let your end user mess with your output calibration there. So output limiting. So QSC amplifier limiting applies automatically with intrinsic correction when you're using our digital amps, but use a peak limiter on the output if you have to go to a downstream device to kind of limit that from clipping accidentally. With proper gain structure, 3 dB full scale is a good limiter threshold. And then essentially output calibration. So use the analog output gain setting to adjust the max output level to the clipping point of the next device in line. And that's important to know what that next device in line is. So anyways, with that, you will get a link for a follow-up quiz. It'll give you 0.5 Avixa credits. Within the next week, our marketing team's been really good about you'll get a recording of this video, you'll get a PDF copy of this presentation, and you should get a link to take this exam. So any questions? I know I ran right up against the hour, but
we do have one question in the chat, Dan.
sure.
Best way to balance simultaneous audio from ceiling microarrays and wireless mics so that wireless mics are prioritized over ceiling.
Wow. So let's see. What the best way to balance simultaneous audio from microarrays and wireless handheld mics so that the you could. I think it could be a method of how you put that into maybe a gating mic mixer. You may want to gate. You may want to actually put the ceiling mic array, if you've got multiple lobes coming off of that, have that go into one gating mic and then the other in there, and then do some type of level priority on the outputs of those. So there's a couple of different ways I think you could attach that. Anything you're thinking of, Kelly, that I'm not, or?
The other thing is you could make it so that it doesn't actually be affected by the gate. So it's kind of like a priority mic, right? Kind of like you were talking head of the table versus other tables. That would be one of the ways I would look at doing it.
Yeah, if you just had maybe 2 handhelds for Q&A, right? And you want them to pop above what's going on, you just put them into the gate. That works as well too. So yeah, we answered that one live. We'll dump it out of there. Preston says most consumer AV receivers come with a room setup tuning calibration. Any similar Q-SYS product for creating a best attempt starting point? No, I don't think, not really. I mean, it's there has been a lot of talk about self-EQing rooms and things like that. And I know that us, along with several other people, have been have worked on things like that. Like, hey, how could we do this automagically? And there are some cool programs out there. Don't get me wrong, like where you know, at 3 a.m. it injects pink and white noise into the room and then makes some adjustments. But we don't have anything like that there. So, any priority ducker recommendations to prioritize hand-mounted mics over ceiling mics? So James has a similar question there. I never thought of using a priority ducker. You know, you could just because the ducker doesn't have to duck at 60 dB. You could say that's a good idea too. So I would auto mix my handhelds and my beams from the ceiling mics, and then put the two outputs of those into a priority ducker, and whatever the priority is, right? You don't, it doesn't have to duck it all the way to the weeds. So yeah, good. That would actually work. We have a priority ducker that will do that too. So let's see. Someone beat me to it. Good job, dude. Well, we got it. Never hurts. Tyrone says, can we use dynamics or processing before the auto mixer? Does it matter? Before the auto mixer, dynamics in that are fine. It's fine to have EQ and things like that. You just don't want to be gating it before there.
And don't do it before AEC.
Yeah, just don't do it before AEC. But yeah, your auto mixer, it'd be perfectly fine. So how should we go about adjusting input gain structure for loud singing vocals? That's where you want to put a compressor in, right? So the idea of the compressor is it works. It's very aggressive for vocals. That's where you really want to use it, because with a compressor, you feel the magnitude of the increase in the voice, but it doesn't increase the level, right? That's kind of how the compressor works in there. So compressors for singing, AGC for kind of program sources or conferencing, if you're good at setting AGC up. If you just need to control any loud booming people, you can just drop a compressor in a conferencing situation as well too. So James Carr, going to the far end of VoIP. Yeah, I think we got you. We got James taken care of. So anyways, appreciate all of everybody joining it. It's crazy to me. I mean, I say people can always benefit from a refresher in gain structure and how AEC works, right? And I've been doing this now since, well, I think we started it regionally in 2021, and then full-time in 2022. So almost 3 full years we've been giving these deep dive webinars, and I rotate gain structure, AEC, and this combo class at least 3 to 4 times every 6 months, and we still always have a bunch of people. So glad everybody made it, and
Thank
happy
you.
everyone can join. Sorry to take you extra 2 minutes here, but hopefully it was worth your time.
We started 2 minutes late, so.
Oh, there you go. There you go. All right. Well, everybody have a great day, and we'll talk to you later. Thank you.
Thanks, guys.